So, so I'm actually recovering from a particularly nasty car accident at the moment, hence the eye patch. But I checked in with my rehab therapist, and they said that this definitely counts as rehab. So I'd like to start by thanking you all very much for attending my rehab session and helping me out here. This talk, I want to talk about exploring complex data with Elasticsearch in Python. But as I put this talk together, I realized that I wanted to do something a little bit more ambitious. And so what I want to do today is introduce you to a new design pattern, which I'm hopefully coining. I don't think anyone's coined this one yet. Now, the interesting thing about design patterns is you don't have to invent anything at all to coin one. You just have to observe something that other people have invented and be the first to slap a name on it. So that's my stance today. I'm trying to be the first to slap a name on a way of building software. And so as I was thinking about this, I realized that this is a design pattern that I've been encountering for 11 years of my career now. So I wanted to start by taking you back in time. There'll be a wavy effect in a moment, from all the way back to 2005. When I had my first job out of university, I went to work for Yahoo, and I spent the first couple of months at Yahoo working with the Flickr team. Now, Flickr at the time was going through some really interesting scalability problems, because in 2005, no one really knew how to scale websites. You know, this wasn't something which people were doing all of the time. So the Flickr team, with their astronomical growth in their photo service, were having to figure out a whole bunch of scaling principles pretty much from scratch. And if you're interested in that, there's actually a book called Building Scalable Websites, The Flickr Way, it says in the corner, which is by Cal Henderson, the CTO at Flickr. And it's pretty much everything that they learned about scaling in building Flickr. It's quite an old book now. I still think it's super relevant. It's a really good read. So I joined Flickr. One of the things that Flickr were doing at the time is they were sharding their database. You know, they started off, they had a single database with everyone's photos in. With the kind of like stratospheric growth they were getting, they decided to divide their database so users 0 through X thousand would live on shard 1, X thousand through Y thousand would live on shard 2, and so on and so forth. And in doing that, you know, that's a great way of scaling up if you've got data that belongs to individual users. The problem is that Flickr's signature feature at the time was tags. So you could tag your photo with raccoon and then go to the all photos tagged with raccoons page and see every photo on Flickr tagged with raccoons. Now, that's pretty easy to build if you've just got one database. If you've got 23 sharded databases, it becomes a lot harder to know how you're going to run that query and get all of that stuff together. And at the time, Yahoo had been on a bit of an acquisition spree. One of the companies they'd acquired had built an internal search technology called Vespa, which was beginning to be rolled out within Yahoo for all sorts of things. And it was exactly the kind of thing that, and in fact, today, if you look at Elasticsearch, it's very similar to what Vespa was able to do 11 years ago, only Vespa never made it out as open source. So this is a diagram from a presentation given by Aaron Straub-Cope, one of the engineers at Flickr. And he's showing that essentially the way they solved their problem is they had all of these shards with individual user data on, and then they had a document index, a big search engine running on this piece of software called Vespa, which they would copy and denormalize all of those photo information, all of that photo information into. So then when you ran a search, if it was a global search, if it was across everyone's data, it would go to Vespa. If it was just against your stuff, they'd run it against the database directly. And so that philosophy for me was something of that was pretty eye-opening, because the problem with any kind of search index is that it's going to take some time for changes in your database to be reflected in search. If you're lucky, it'll only take a few seconds, but it might take longer than that. And the great observation that the Flickr team had is if you're looking at other people's stuff, that just doesn't matter. You know, if somebody else has uploaded a raccoon photo and you don't see it when you look at all the photos of raccoons, you're never going to know. But if you're looking at your own stuff, this can be a total crisis. You upload a photo and it's not on your page, you think the website's broken and you upload that photo again. The same thing if you edit a photo and add tags and then those tags aren't showing up. So if you're looking at your own stuff, it's crucial that you have the atomicity and the transaction safety of a relational database. But if you're looking at other stuff, those few seconds of lag are just invisible to people. So this becomes a really powerful way of handling a whole range of other types of queries. So I promised you a design pattern. I've called it the denormalized query engine design pattern. Feedback on that is welcome. But basically, the idea of this is if you're building a sort of highly scalable piece of web software, and I guess it would work for non-web software if you want to build apps and things as well. But anything with large amounts of data, you start off with a point of truth, which is a relational database. You keep it as normalized as possible. You could use like a modern NoSQL thing, but as far as I'm concerned, you need to have a really good reason for ditching relational databases at this point. It turns out they're really, really good. So you keep your normalized data in there. Then you denormalize any relevant data to a separate search index running on something like Elasticsearch. Now, I say all relevant data. Really, this is a lot of the art here is in picking what things are going to go in there. Which of your tables should also be reflected in search? Which fields from those tables should be reflected? Making sure that you can power as many interesting queries and features as possible while still keeping it practical to keep that connection going. Then the place where you invest effort is in the synchronization. The biggest problem with this kind of setup is making sure that any changes that are applied to your database are reflected in that search index as quickly as possible. And I'll go through a few different techniques that I've used throughout the last 11 years for doing that towards the end of this talk. And when you're asking questions of your data, this is where you get smart about the routing. You can say, OK, this is something which is best served by my relational database. Like I said earlier, one of the key things there is if a user is looking at their own stuff. Or this thing might be something which is better suited to running against that search index. And that really, a lot of that depends on your tolerance for that latency in updates. And then an optional thing which I like doing is when you run queries against the search engine, it can give you back all sorts of data. I like to have it give me back the primary key and the object type of the actual thing that's being returned. And then I'll look that up directly from the database before displaying that. So that gives you a little bit of additional overhead because it means that you run the search and then you run a query to fetch things from the database and display them. But it eliminates any risk of showing stale data. And it's something that's pretty easy to scale. But once you've got a primary key, you're doing a primary key lookup. Databases are pretty good at those. If you can have you can have a master replica set up so that you can run queries against replicas. You can add caching. There's all sorts of ways that you can make that efficient, and it eliminates that risk of serving stale data. You can actually go a step further, and this is something we do on Lanyrd. If the search engine returns an ID that is missing from the database, that probably means that the record's been deleted, but the delete hasn't gone through to search yet. So at that point, we'll queue up a Celery background task to delete that item from the search index as well. So this is the design pattern which I'm basing this whole talk around. And so why would you do this? So I touched on it a little bit talking about Flickr scaling problems, but pretty much the key thing I want you to take away from this talk is that search engines are not just for text search. Things like Elasticsearch and Solr are very good at running text search. It's one of their specialities. But it turns out there are all sorts of non-search related things that they can do as well, which are super powerful, and they can often do better and faster than relational databases. So in exchange for that enormous amount of engineering effort in synchronizing the data, and then those few seconds of indexing delay, you get the ability to horizontally scale those queries. It's much easier to horizontally scale a search engine than it is to scale a database. You get some very powerful new types of query, and I'll try and touch on some of those as the talk continues. And you also get aggregations, which is a feature that Elasticsearch in particular is very good at, which gives you all sorts of ways of doing statistical analysis of your data as well. So in the talk title, I promised I'd talk about Elasticsearch. I'm going to talk about Elasticsearch. Elasticsearch is, I guess at this point, it's probably 4 or 5 years old now. I believe it to be the most interesting of the open source search engines. I used to be a huge fan of Apache Solr. I still think Solr is great. But I kind of see Elasticsearch as what Solr would look like if you designed it today. So if you were going to build a search engine today, obviously it would be JSON, it would be HTTP. You wouldn't bother with any XML or anything. You'd have everything happen over HTTP, and that's how Elasticsearch works. And when I first tried it about 3 years ago, I tried building something quite interesting on top of it, and then the index corrupted, and I lost a month's worth of collected data, and I got a bit grumpy. That was in the Elasticsearch 0.9 days. It sits here at 1.0. It's actually past version 2 now, and it's stable enough that a lot of very big companies like GitHub, are happy to rely on it. So I have no qualms at all recommending it, despite having been burnt slightly by it a few years ago. So Elasticsearch, a few key things to know. It's an open source search engine. It's built on top of Lucene, which is pretty much the cutting edge of open source search libraries. It's a set of Java libraries. If you go to any university who's doing research into search-related stuff, they're probably building on top of Lucene. There's a lot of very good computer science embedded in there. it takes that library and it makes it available over HTTP with JSON, which is great because it means that you can easily use it from basically any modern programming language. If it's got an HTTP client and a JSON parser, you can talk to Elasticsearch with it. The marketing claims to be real time. It's close enough. Like, we're talking within a couple of seconds of a document being posted, it shows up. So if they want to call it real time, I won't necessarily push back too hard on them. The query language is a DSL, a domain-specific language in JSON, which is incredibly powerful. You can do it's kind of, it's got pretty much the same kind of flexibility as SQL, only it's in JSON, so it's a little bit weird. But you can get a lot of very cool stuff done with it. They have a very strong focus on analytics in addition to text search, which is where a lot of the more interesting use cases come out of. And then finally, the elastic in Elasticsearch really does mean elastic. It's highly horizontally scalable. When I first started playing with it at Eventbrite, I set up a cluster of 3 Elasticsearch servers. And the way you do that, you start at one, and then you start a second one pointing it at the first, and they just magically rearrange documents across them and start load balancing and things. And then I fired 1 million documents into it, and I watched them get spread across the 3 different servers. Then I shut down one of the servers just to see what happened. And within a couple of minutes, the remaining 1 million documents is rebalanced across the other 2. When I started the third one up again, they rebalanced again. So they're actually plugins that will visualize the way the documents are distributed. But it's really impressive how seriously they take that horizontally scalable aspect. And like I said, a lot of big places are relying very heavily on it now. So it's pretty fantastic on that front. So that's enough of the sort of high-level theory. Let's actually write some code. Let's build a search engine. The most basic example I can think of, this one will be about full-text search. Let's build a search engine for the Django documentation. So the Django docs are written in restructured text. They're a bunch of files in a directory structure. If you download Django as a tarball, you'll get them in a subfolder. So in writing this code, this is very, very basic Python. It's not doing anything exciting. Here we've got a classic Python directory walker. It's going to walk over that folder full of files and find any file name that ends in .txt. And for any of those file names, it's going to extract a few interesting things about it. So figure out the path to the file, open it up and get the content, extract the title, which is a regular expression, which is left to your imagination, but I'll share the full code later. And then it yields a Python dictionary, which is essentially a JSON object with the title, the path, the top folder, the URL, the content, and I'm using an ID. I'm using the SHA-1 hash of the URL just to have a unique ID to feed to Elasticsearch. And then I'm not even going to talk to Elasticsearch from Python for this example. All I'm going to do is print out a bunch of JSON. So Elasticsearch has a bulk import mechanism where you can send it a line saying, I want you to index a document with this ID, and then you send them the document, and that's it. And what that looks like is this right here. And in fact, I'm going to take a risk and do the live demo of this. So when I run my Python script, here we go. It just, I'll pipe it through more so you can see that. So it's run through, it's walked over the Django docs. It's saying, index this document with this ID, title, Django documentation contents, URL, contents, etc. As we go down, it's indexing all of these other, so it's indexing all of this stuff. And then what I'm going to do is I'm going to pipe it to curl. So here's that line again. I'm piping it to curl. I'm doing a post to Elasticsearch, which is running in port 9200. This bit here is the name of the overall index. You can make anything up you like there, because Elasticsearch will create an index for you if it hasn't heard of that before. This is the name of the document type. I'm calling it doc. And I'm using the _bulk endpoint, so I'm telling it to expect this particular format. And then -- data - binary @ means whatever's piped into me send as the HTTP post body. So I'll do that. And this is Elasticsearch replying back, telling me that it's successfully indexed all of these documents. And having done that, I can actually run some searches. So here we go. This is, actually, is that large enough? So here I'm saying run a search against that index, and this is giving me back all 370 indexed documents. I can say $q equals prefetch related, and it'll give me back 11 documents. So these are the 11 documents that mention Django's prefetch related function. If we look through these, you'll see that most of these are actually release notes, because I guess prefetch related gets updated in lots of different releases. So let's be a little bit more interesting. I'm going to add -top _folder : let's just use the auto-completed one here, minus top folder releases. So that's excluding things where the top folder filter field matches the word releases. And that's given me two things. And one of them is the API reference. And one of them is, where's the other one? Oh, you know what? I think I can just collapse this. And one of them is the database access optimization page. So this is, as you can see, the amount of code involved in getting this into Elasticsearch is pretty trivial. And having done that, even though we're not using any advanced features, we actually have a usable search usable search feature. Now, what I'm not showing you here is the Python code you would use to actually turn that into an interactive website. But I'm sure everyone in this room can imagine what that would look like. You know, you construct a URL, you fetch it, you get back the JSON, and you can process it and use it to build whatever kind of pretty web page you like. So in the talk title, I foolhardily promised that I'd get to something complex. This is my complex example, and it demonstrates a few more of the advanced features of Elasticsearch. And what I ended up doing was looking at the Python package index, PyPy, where whenever you do easy install or pip install X, it's pulling it from that data. Turns out PyPy has about 86,000 packages in it, and every single one of those packages has JSON metadata, which is available just by sticking /JSON on the end of the URL on PyPy. So I set my laptop running overnight to crawl all 86,000 of those JSON files, and it gave me an interesting data set to start exploring, to index into Elasticsearch and start exploring. So you can see here we've got things like the maintainer's email address, the number of downloads in the last week, what packages it requires, and then these classifiers, which are kind of an interesting way of introspecting that data. So the previous example I showed you with the Django documentation relied on an Elasticsearch feature called dynamic mapping. Basically, Elasticsearch guesses the structure of your documents when you send it over there, which is super convenient for building something quickly, but actually it's not a great way of using Elasticsearch in the long run. You know, when you're building something properly, you need to treat dates separately from integers, separately from text fields. There might be certain text fields that you want to properly index for things like stop words and so forth. Other text fields are maybe atomic values that you don't want to do that for. And so Elasticsearch lets you define a mapping. You can do that using the HTTP API. So if you do put against the name of an index and then the name of a document and then underscore mapping, you can send it a JSON document describing the the kind of documents that you want to index. So here I'm saying it's got a string called keywords and a string called summary, and it's got a string called name, which is not analyzed. So the name, which will be a string, would be something like simple JSON, shouldn't be stemmed and cut up and so on. And it's got classifiers, which also aren't analyzed, and description. The analyzer snowball is the analyzer that's used for the stemming and stop words and so forth. Now, this little mini language isn't enormously unpleasant, but it turns out in Python there's a much, much better way of working with this. There's a library called Elasticsearch_DSL. It's a Python library that's actually supported by the company behind Elasticsearch. And what that lets you do, it looks very similar to the Django ORM, which I think was part of the inspiration for it. So you can create a subclass of doc type, define a bunch of fields in there, like name, summary, description, keywords, classifiers, tell it which index it should go in, and that right there, that piece of Python code is enough to completely replace this JSON and set up that mapping for you. So once you've done that, you call package.init, and that'll do the put and send the JSON up and set up those documents for you. And then to actually save an object, you construct the class, feed in the name, the summary, the description. You feed in the ID if you want to send it an ID as a subproperty of the meta dictionary for some reason. And then you call .save at the end, and that will send your document up to Elasticsearch and save it there. So given that, let's switch over to another demo and actually show you what some of that looks like. So Elasticsearch is, as I said, it's all done over HTTP. A slightly bizarre thing about Elasticsearch is that it uses GET requests with a body. So I didn't even know you could do this. It turns out post requests, you can send a post with a body, and that's fine. It turns out you can actually do that with GET requests too. Elasticsearch is the only piece of software I've ever seen that uses this ability, but it means that you can run a GET, which is semantically correct because you're querying the data, and you can still send a complex JSON query as the body. So this is a piece of software called Sense. It's because you can do all of this stuff from curl or using Python or whatever, but this is a custom user interface designed for querying Elasticsearch. And so you can essentially type in an HTTP command like get package/search, click the play button, and it will run that query against that index. In this case, I've got the 86,000 Python package index things indexed. If I hit _search without any arguments, it'll return all of them. So as you can see, it's giving me them back. It's giving me 86,000 documents. The index is package, the type is package. It gives me the ID, which is the name of that package. And then the keywords there are interesting. I think somebody might have, I wonder if that's my bug or someone else's. Keyword summary in these classifiers as well. And where this gets interesting is that you can compose more complex searches. So here's a search where I'm saying, pass in this is that JSON DSL I talked about. I'm saying, run a query where we match the description field against the word Django. And if I hit play on that, that'll return 8,749 results. But it's only results where that description field includes the text Django. And you could, it's very easy to expand that query to search multiple different fields, to boost certain fields over other fields, to do a whole bunch of different interesting things. But the feature that most excites me personally about Elasticsearch isn't actually the querying stuff at all. It's a feature that Elasticsearch calls aggregations. If you've worked with Solr, you'll have seen these called facets, I think, instead. And the best way to discuss those is really to show what they do. So let's run that search again. This is a search against all documents. There's 86,000 of them. But here I'm saying that I want to do an aggregation where I want to call it classifiers, and I want it to be a terms aggregation on the field classifiers. What that means is that if you scroll to the bottom, Elasticsearch has added in counts for the individual classifiers that are available across all of those documents, and it's ordered by frequency. So it turns out intended audience developers is attached to 37,000 of those documents. Programming language Python is 34,000. OS independent is 24,000. Python 2.7 is 23,000. And that list, but what's happening there, I think, is the thing that really excites me about this is if you wanted to do this against a relational database, this would not be a cheap query. You know, this is something which you'd probably want to do in a background task or even not do at all. Because of the way Elasticsearch and search indexes in general are constructed, actually pulling these things together can be done in just a few milliseconds. So building interfaces or building tools that do these complex aggregation counts across giant amounts of data suddenly goes from virtually impossible to very feasible, which means that there's all sorts of things you can do to start exploring that data. So I'll show you another example. Hang on a second. Sorry about this. I had do not disturb on. That shouldn't have happened. Oh, well, I'll turn off Wi-Fi. I'll show you a couple of other examples of more complex queries. This one here, this is a query called a more like this query, which lets you say, I want you to take the package called simple.json, so the document called simple.json, and find other things that are similar to that based on the description and the summary field. Use a minimum term for each of 1, maximum query terms 12. There's a whole bunch of additional arguments you can put in there. And you can even put multiple packages in here as well. So I'll hit play on that, and that took 39 milliseconds. Took 12 milliseconds the second time it ran it. It returned 749 packages. And sure enough, the top-rated package as being similar to simple.json is this thing called Dogion, which is a fast, complete, correct, and extensible DSON encoder. Top marks to anyone who knows what DSON is. But you know, it's pretty clear that that is a similar kind of thing to simple.json. And actually, at Eventbrite, we've been experimenting with using this for doing things like generating related events for an event that you're looking at using these kinds of more like this queries. It's a really powerful thing, which, because it's just another query type in Elasticsearch, you can combine that with all of the other Elasticsearch functionality. So actually, let's do that right now. I'm going to throw in the aggregations again. Here we go. So now it's going to say 749 documents, but at the bottom, it's telling me that of those, 371 were Python 2.7, 296 were Python 3, 216 are defined as production stable. So again, we're taking this collection of documents, but we can start gaining all of this additional insight from it using these aggregations. Now, when I indexed the, I'll actually pull up an example of, oh, I can't because I've got the, so it turns out the Python package index doesn't just have individual packages. For each package, it lists releases as well. So it'll show you, say, for example, that Django had release 0.9 and then 1.1 and 1.2, and each of those releases had this number of downloads. There's a huge amount of historic data in there. So I've indexed that stuff as well because it lets me illustrate a few other things that we can do here. So here I'm going to do a search against the releases rather than the packages. Here we are. It's returning 659,000 of them. It turns out the Python community is very prolific. And you can see that there's the package 3LWG had a release that was version 4.0 on the 3rd of July 2014. And if we can but we can then add these aggregations saying, OK, the package name for this was 3LWG. So maybe 3LWG had a bunch of other packages other releases associated with it. And the magic of Elasticsearch aggregations is we can then see this list at the bottom showing which are the packages with the most releases. So it turns out Frida, Frida, has 2,115 releases release files listed on PyPy, making it by far the most prolific. I looked into that. The reason for that is it's a piece of software that bundles the Windows compiled version as well as the OS X compiled version and bdists and so forth. And since each of those gets counted, the fact that they released 20 versions each time adds up to a really big number. So you'll notice that when I run this aggregation, I actually don't care about the results at all. I'm getting all of these hits, and I'm having to scroll down to the bottom. If we stick size:0 in as one of the arguments, then we can just get back the aggregations. And so this is how you'd go about doing a more interesting visualizations or other sort of introspections of that data without having to worry about a bunch of pointless search results. And then I will show you one last example here, because it's kind of fun. Aggregations can be nested. So in this case, I'm saying, get me all of the releases, aggregate them by the package name, so Pillow or Django or whatever, and then add, for each of those package names, do an aggregation on the sum of the downloads field on those packages. So actually, I'll take this off to demonstrate. So you'll notice each of these packages says downloads 3,154. So that was downloaded from PyPy 3,000 times. If I run this query here and scroll to the bottom, we can see that libsass, for example, has been downloaded 421,000 times. Shapely has been downloaded 1.7 million times. And again, this is a calculation that is running against all of that data in Elasticsearch. And again, this isn't something you'd want to do in a relational database, but against 600,000 documents in Elasticsearch running on my laptop, it's the results are coming back instantaneously. Just one last example around this. You can actually, here we go. You can sort by that, you can order by that sub-calculation. So here I'm saying, group by the package name, order by the number of total downloads descending, where total downloads is this other calculation. If I run that, we'll see that the most downloaded package on PyPy is simple JSON, which has been downloaded 192 million times, apparently. Setup times is only 103 million times, so simple JSON is clearly, which, considering that the JSON library has been included in Python since Python 2.5, is kind of impressive, but there you go. So I hope that gives a good sort of illustration of the kind of things that you can do with these aggregations. Now, that's Sense. Sense is kind of where I spend most of my time when I'm playing with Elasticsearch. It's a very useful tool for trying things out. The fact that it saves all of your previous queries means it's easy to bounce up and down and try different things out. But the other tool that Elasticsearch offers, which is kind of mind-blowing, is called Kibana. And so Kibana is essentially it's an interface for exploring your data that, given a chunk of data in Elasticsearch, will just give you a whole bunch of UI tools for free. So let's use that. We'll run that first against the this packages database. So by default, I run Kibana. It says, well, we've got 86,000 documents. It shows me the documents, and I can expand them out and see each one of them. If I click add on these, so I can say name, add, and did that work? There we go. Name, description, and type. So you can build up columns to see things that way. But where this stuff gets really exciting is when you do things like look at classifiers. And I showed you how to do this from the JSON level, but here, when I click on classifiers, straight away it starts showing me the most popular classifiers for this search. So I'm seeing the intended audience developers, the programming language Python, and so on. And if you visualize at the bottom, it'll turn that into a bar graph. So again, my setup for this was literally downloading Kibana and running it. I didn't have to do anything else other than point it at my index. And already I'm getting graphs out of that index of interesting insights into that data. I can click on these. So now I've said, I only care about Python 3. I only care about MIT approved. And now it's showing me that for the Python 3 MIT licensed things, the most popular tags are these. There are like 1,359 documents that are in development status alpha. It's this really powerful way of exploring the relationships in your data. And again, this is essentially for free. Once you've got Elasticsearch up and running, the Kibana interface just starts working. I'm going to switch over to releases again. So the other thing that Kibana is really good at is working with time fields. You can take a set of documents and give each of those documents a timestamp, and Kibana will then be able to automatically create you time-based histograms and things. The releases from PyPy each have an upload date on them. So I've configured the upload date as the field that sets the as the time-based field for this. Now, if I ask Kibana for the last 5 years, we can see this is an instant graph of the number of uploads that have been made to PyPy per month. So we can see that back in 2011, there were about 2,800 releases a month. These days, it's more like 21,000. So PyPy release traffic has gone up by a factor of 8 in the past 4 years. But again, I really didn't have to do anything to get this. I didn't have to do anything fancy at all to get this. This is just falling naturally out of the fact that my data is available in Elasticsearch. And anything that you can do in Kibana, you can do in your own Python applications. You can actually, Kibana's just using JSON over HTTP. So if you fire up the Chrome inspector, you can even capture the queries that are going on. In fact, let's try that now. There we go. So here is a query that was just sent through to Elasticsearch. If I wanted to, I could copy and paste that query directly into my own code base and replicate this Kibana query very simply from Python. So this is where the exploring complex data stuff gets really interesting, I think. You can take basically any data set of any size, because Elasticsearch scales horizontally, load it into Elasticsearch, point a tool like Kibana at it, and you can start getting really interesting insights into your data. And so I've got a screenshot from the Kibana documentation, which illustrates that in a bit more detail. Here we go. So Kibana has dashboards built in. Kibana's original purpose was actually for log file analysis. There's a piece of software called Logstash that the Elastic company have released, which can take your log files from Apache or Nginx or whatever and fire them into an Elasticsearch index. And then you can use Kibana to get almost real-time graphs of number of hits to your website, number of unique IP addresses. You can geolocate it and map against like a live updating heat map of places that you're getting visits from. And what I like about this is the fact that this was designed to deal with log files where you could be getting tens of thousands of updates a second really emphasizes that this is meant to scale big. You know, if you've got 90,000 packages on PyPy, that's nothing compared to the web traffic logs of even a moderately successful website. And so these tools really are amazingly powerful for getting insights out of both time series data and regular data sets as well. So I promised I'd talk a bit more about the hardest problem in this design pattern, which is synchronizing your database with Elasticsearch. So I'll talk about a few techniques I've used on projects over the past few years, which I've had some level of success with. The first one, this is how we did this. This is what we did for Lanyrd. So Lanyrd uses this pattern very extensively. And the way we ended up doing it is we have a Boolean flag in our Lanyrd model, so a column in the database called needs indexing, and it's a Boolean field, and it's got an index on it. And the idea is anytime you save a change to a model, it automatically flips that to true. and then there's a cron job which runs every few seconds, which grabs everything from that index table that needs indexing, pulls that from the database, reindexes it, pushes into Lanyrd actually running on Solr at the moment. It's not upgraded to Elasticsearch yet, but it pulls everything, indexes in the database, and then writes that field flag back to false. And the reason that's one of the reasons we did this as a flag is often one of the challenges in this kind of work is that you don't just need to reindex when an individual row changes. Often there are dependent rows for which you need to change things as well. A simple example might be there are like 20 conferences at this particular venue. If you want it so that when you search conferences, the venue name will show up, then if somebody changes the venue name, you need to mark all of those conferences as being updated as well. And so we do that for the guides feature on Lanyrd. We have a piece of code that says, get all of the conferences related to the guide when it's updated, and set the needs indexing flag to true on all of those at once. And it can lead to a sort of right magnification thing where you can change one thing and it might cascade to 1,000 rows. But since you're doing this as a batch job anyway, it doesn't really matter. And that tended to work out. So this technique, I've used it. It's worked fine. There's a slightly different technique which I would recommend if you're going to go with this kind of thing, which is that instead of using a Boolean flag, use a last touched date time field. Again, database indexed with defaulting to now, and you set that to the current now date whenever you need to flag it. The reason for this is that sometimes you'll want to have more than one search index running off the same database. If, for example, you're about to launch let's say at Lanyrd we decided we wanted to ship Elasticsearch, we'd want the Elasticsearch database to be able to keep track of how many updates it's applied separately from our Solr search engine. And with a Boolean flag that's recording like either yes or no, you can only use that against one index. If you've got a date time field, your index can keep track of what the last touch time it saw was, and it can query for things since then. So it basically means you can have more than one indexing operation running against the same database, which is pretty useful. Another mechanism I've been using on a more recent project is to keep this completely independent from the database and instead do it using a queue. So Redis is a great solution for this. Kafka works really well as well. Basically, anytime an object needs reindexing, you put that object's type and ID in that queue. So you say, here's the thing that needs indexing. Here's another thing. Maybe there are 20 things modified at a time. You stick them all in the queue. And then you have a job which every few seconds clears the queue, dedupes those things. So if something was mentioned multiple times, it'll only get indexed once, fetches them from the databases and re-indexes them. And it's more complicated than having a database flag because you need to be running a separate queue system and so on. But it's not too difficult to get set up and running, and once you've got it up and running, it works really well. Then the most interesting way we've done this, and this is something we've been doing at Eventbrite, is the problem we had at Eventbrite is there was just too many different places in the code that might be modifying something in the database. You know, there's a bunch of legacy code. There are all of these different systems. We've spent the past few years actually sort of refactoring these into a service-oriented architecture and cutting down these code paths. But you still can't be sure that there's not some cron job that someone in accounting set up which is modifying a field on a row somewhere. So the single point of truth at Eventbrite for what's changing is the MySQL database. It turns out MySQL has replication. And the replication stuff happens through a thing called a replication log, which is a stable enough format that you can talk to it not just from MySQL. There's a Python library we found called Python MySQL replication, which you can point at a MySQL database, and it will listen to the replica queue and let you process those events as they come through. And so we built a system called Dilithium. And what Dilithium does is it subscribes to the MySQL replication log, listens to changes to various important tables, and whenever it sees one of those changes, it translates them into an interesting moment, like order 57 has been updated, or venue 36 has been edited, or event 59 has been added. And those interesting moments are then written into Kafka, which I won't talk about too much today, but it's a very, very robust high-performance queue for exactly this kind of use case. So having done that, our re-indexing code, which updates our Elasticsearch index, just subscribes to that queue in Kafka, and when it sees that event 57 has changed, it fetches event 57, re-indexes it into the database. It's relatively early days, actually. We only turned on We turned on the search engine stuff a few months ago, I think. But it seems to be a very robust way of handling this. And like I said, this is a great way of working with legacy data sets where you can't guarantee you're going to pick up on everywhere that the change might be happening. So I'll talk about a few more use cases for Elasticsearch, since we're talking about Elasticsearch. The first one, this is my personal favorite, is what's called faceted search. So I'm sure everyone here has seen an interface like this. You know, if you're shopping on Amazon, you type in power plug, it'll give you a bunch of things down the side saying there are 57 items in the electronics category and 32 items in homeware and that kind of thing. And so on Lanyrd, we do that. If you search for Django on Lanyrd, we'll show you 3,000 results. But of those, 384 of them are people, 334 are conferences, 6 are topics. If I click on conferences, oh, blast. I'll turn that back on. If I click on conferences, now it's just showing me those conferences. It's now showing me that 252 of those conferences are in Europe, and 84 of them are in Central and Eastern Europe. So if I click on there, I'll see that there is a very enthusiastic Django community in Poland and one in the Czech Republic. And these are, again, this is me gaining insights into that data just through a very simple UI that lets me explore through things. I can also see that 20 of those are tagged user groups. So here are user groups that match the term Django and are taking place in Central and Eastern Europe. And you know, I think this is a fantastic way of taking a huge, complex data set and making it explorable and allowing people to answer questions with it. I do find whenever I talk to a designer about this and try and convince them to add little numbers next to the filters, they always push back on it. So maybe it's a nerd thing, and regular human beings don't like this. But I think it's a pretty compelling way of building an interface for exploring data. Next example. This, again, is something we've been playing with a lot at Eventbrite. As I said earlier, search engines really aren't just about full-text search. One of the really interesting things you can do with them is build recommendation systems. So Lanyrd, key way of suggesting events for you to attend is it looks at the people who you follow on Twitter, and it shows the events that those people are speaking at or going to. And the first version of Lanyrd did that as a database query. That lasted about 3 days, and then we got linked to from TechCrunch UK, and the entire site crashed. So at that point, we explored switching over from doing it against SQL to doing it using Solr, again, another search index. And it turns out that if you compose a search against Solr Elasticsearch that says events where saved by or attending matches user A or user B or user C or user D, and you can have like 1,000 user IDs in that query, and it just works because search engines are optimized for exactly that kind of lookup. So doing those sort of social queries is actually really easy. I mentioned the related content stuff, the more like this query earlier. At Eventbrite, we've started looking at, so we've been experimenting with recommendations based on events that are similar to the last 10 events that I have saved. And again, that's just using the more like this query. You can throw in extra filters saying, and are within this geographical region, and are happening in the future, or and are happening in the next few weeks. But that, again, it gives you a really powerful way into a recommendation engine that's essentially free once you've got your data denormalized into search. And then the final thing, the other reason that this is great for recommendations is search engines are really, really good at scoring. Right? Their whole purpose is to show you the most relevant stuff. So you can run a query where you say, boost this by events that are in a certain city, boost it by events that have been saved by my friends. You can actually come up with very complex ranking algorithms which fit naturally into the way search engines work. Another thing I'm really excited about is analyzing user activity. I mentioned earlier that Elasticsearch and Kibana works really well for log analysis. And if you're building your own website, you can go a step further and have your own index of key actions and things that your users might have done. So you might have a custom index where you write in, user executed this search, user followed this other user saved this thing. And because it's in Elasticsearch, unlike just being in a log file on disk somewhere, you can write features that query that interactively for those users. So you can then start building application logic that will vary depending on recent actions your users have taken. This is the kind of thing which, without something like Elasticsearch, if I suggested that you build this, you'd probably say, yeah, but that's going to take us months, and we'll have to add new data stores, and it's just too inconvenient. It's too much work for the amount of value we'll get out of it. If you've got something like Elasticsearch in your stack, these features become so much more inexpensive that it becomes it becomes feasible to start exploring them. And then this one, analyzing patterns. I've shown you some examples of this already with the way I was clicking around through the Lanyrd search. Because Elasticsearch is so good at saying the people who match this criteria also match this and this and this, it's a great way of exploring your own data sets. So one thing we tried at Lanyrd is we essentially assigned characteristics to our users. So things like, this is a user who has used LinkedIn. This user signed up in this year. This user was referred by a friend. And when you've got all of those loaded in, you can then start using something like Kibana to say, OK, so which of our users are more valuable? Is it the ones who use LinkedIn or the ones who use Twitter? Is it, which year gave us the most impressive set of signups? So exploring those interesting relationships, it's one of those things that is super inconvenient unless you have the right tooling, and then becomes something that can just be a daily activity. I wanted to close by mentioning why this stuff even works. There's a little bit of theory that this was one of those things where once I understood it, I had a much better understanding of why this is valuable. If you think about the problem of search, it's basically a set intersection problem. If I search for skateboarding dogs, the search engine goes and says, OK, find me all of the document IDs that mention dogs and all of the document IDs that mention skateboarding, and intersect those two and give me back those results. So Elasticsearch is optimized for doing exactly that type of query. That means that any other query that can be turned into a set intersection, like a geopolygon search, where you can say, OK, that polygon matches to this set of documents, just becomes something that it can handle really quickly. And it's distributable. You can run an Elasticsearch cluster with 20 shards and ask a question of those shards, which will get mapped out across all of them. The sets will come back, they'll be intersected, and they'll be returned to you. Relevance, as I mentioned earlier, is a first-class concept. But really, if you look at large-scale Elasticsearch, it's essentially doing the MapReduce algorithm that's famous from Google's whatever Google called their thing, and Hadoop and so forth. But unlike Hadoop, where you submit a job and wait 30 seconds for results to come back, Elasticsearch is giving you results in 50 milliseconds. So all of that sort of magic scalability and those interesting aggregations and so on really come from the fact that if you build everything on top of set intersections, you can be really, really quick. So my summary, you should denormalize your databases to a query engine. Elasticsearch is pretty good at that, and I've got just a few minutes for questions. So thank you very much.
Thank you very much, Simon. Is it on? Yeah. Okay. So my question for you that I often get asked is, why would you not store everything in Elasticsearch as your primary data store?
So the question there is, why not store everything in Elasticsearch? Partly it's a trust issue. I trust relational databases. Like, the entire purpose of relational databases is not to lose your data and not to allow people to corrupt your data and so forth. Elasticsearch, it doesn't lose data very often, but I wouldn't say that it's their defining goal in building it. And then the other thing is that like relational databases have transactions. Elasticsearch, there's those few seconds of delay. It's not really a completely atomic data store. So you're welcome to, and in fact, people do build cool things on top of Elasticsearch where all of the data's in there, especially log analysis and so forth. But I kind of feel like if you're building a real application where the data matters, you should be using tried and tested technology to keep it safe. OK?
I got a couple of questions. I got a client with with Elasticsearch in the past. One big problem is the balance the shards with the replica loads, because when replica you can have as many as possible. Mm-hmm. But for shards, once you create it, you want to add more. You have to re-index everything. Uh-huh. So I mean, for your side is obviously very big. How you kind of try to balance this, and when you do the MapReduce, map doesn't matter. Uh-huh. But the reduce side, when your aggregation is really complicated, sometimes we'll get a memory issue like out of memory in the Java heap. So we call even call the Elasticsearch COP, and their engineer basically just say you have to very carefully design the aggregation sequence stuff.
So the question there is along the lines of it's around when you're dealing with really complex queries and much larger data sets, there are actually configuration options in Elasticsearch become crucially important, like the number of replicas you have, how you distribute your shards. You are talking way above my pay grade at the moment. We have an entire team at Eventbrite who solve those problems. So that's definitely, when you get there, it stops being super easy. but there is at least a very good sort of supportive community of expertise around that.
Okay. Do your company kind of constantly upgrade the Elasticsearch version? Because they only have like 1 year, support.
I would have to defer to our ops team for questions about that.
I had a question. You said about dilithium, it's really good for legacy data sets.
Sorry, could you say?
Dilithium, you said it's really good for legacy data sets.
Well, the approach that it takes, yeah, which is, so dilithium isn't open source, but the approach of listening to the replication stream is great for working with legacy data sets, yeah.
Why legacy in particular?
Say that?
Like why legacy data sets in particular?
So the problem with legacy data sets is, so in an ideal system, the only one place updates the database. So if you want to find the code that modifies an order, it'll be in one part of your code base, and you can go there and say, okay, I'll add a bit of code that says update the order, and then write a thing to Kafka saying, hey, this order has been updated. But in larger legacy code bases, it's much more likely that just tracking down all of the places that change something is a difficult task. There may be multiple different systems built by different engineers over many different years that could cause a change. So that's why I'm excited about the replication stream thing. It means that instead of spending weeks and weeks tracking down all of the places, you can say, okay, we know the one definitive source of changes, and we can listen to that.
I read that Elasticsearch updates are essentially deletes and creates. So how good is Elasticsearch in handling update-heavy data?
So the question is, how good is Elasticsearch handling update-heavy traffic? I mean, yeah, essentially I can't remember. They were working on an in-place update. I honestly can't remember if they've shipped it yet or not. But yeah, the general idea is that anytime you update, you reindex the entire document. The pattern I'm describing here kind of takes that into account in that when something changes, we don't say, okay, update Elasticsearch and change the title to this. We just say, event 57 needs to be completely reindexed, and we reindex and send it up there. And so if you do that, your write load is a lot higher, but the chance of making a mistake is much lower. And so generally, I found that works pretty well. OK. I can take one last question, I think.
Actually, I have two.
OK.
You mentioned faceting. Isn't faceting kind of outdated right now?
I mean, faceting is an Elasticsearch. Everything that Solr would call faceting has become just one of the many aggregations that Elasticsearch can do. So in terms of the terminology in Elasticsearch is now aggregations, but it solves the same set of problems.
It's the same thing, OK.
Yeah.
So conceptually, it's the same thing. And second thing is that you mentioned that as an optional thing, you could make two queries, one to Elasticsearch, get the IDs back, and do this and so on. I have used Elasticsearch in the past 6 months and abused it and suffered and so on and so forth. One problem I faced with that approach is that when you get the IDs back and you try to do that, you applied some criteria to get the data from the Elasticsearch. And the criteria itself may not match anymore.
That is true, yeah. So it's true that if, for example, I searched Elasticsearch for raccoons, and it gave me back 20 documents, and then I displayed those 20 from the database, but one of those had the raccoons tag removed, yeah, you would get a mismatch at that point.
You would get a mismatch.
So that's, I feel like it's a judgment call on if that risk is worthwhile. I'd say for the raccoons case, nobody's really going to care, but certainly there are some cases where that's not acceptable, and for that you should be hitting the database directly, probably.
Yeah. Okay.
Cool. OK, thank you very much.